Oh. And how... How do I get it to that screen? Like the whole thing? Oh, I'm just trying to display it on, so that my whole, yeah, I want to mirror the, it's on the left. It's on the left.
Oh, okay.
Yeah.
Where did you put? Okay, open setting.
So this, that.
Display. You have arrangement.
Oh, that. Okay. That should. This is good. Good afternoon. First, I would like to thank the FAST Foundation. No. No? Okay. First, I would like to thank the FAST Foundation for inviting me here. This is my first Small Talks conference, so many of you do not know me. My name is Boris Shingarov. I work at Labware. I discovered Smalltalk in November 1994 when I was doing my thesis in quantum fields. So roughly this week marks 20 years of me doing Smalltalk. I've been primarily concerned with VMs, like forever, and mostly for all kinds of targets, from tiny embedded things to big iron. And I discovered that porting them across the board is essentially impossible. Especially today, as opposed to 20 years ago. Today's bugs are complex. Like your bug is caused by things like race conditions. Your bugs are caused by things like contemporary aggressive compiler optimizations. In order to be able to debug these things, in order to be able to produce a virtual machine that actually works across the board, you have to understand the whole range of complexity of all of your targets. That means, let's say, the whole specification, all the details of your microprocessor that you're targeting, that your VM is targeting. But the problem is that no single microprocessor vendor is definitive in this post-uniprocessor era. So let's say you want to port to ARM. Oh, okay. Well, I'm going to read the ARM architecture reference manual. Okay, well, that's 5,500 pages. Okay, there. Good luck trying to understand that. Okay, maybe you somehow, by some sort of miracle, you managed to do it. Well, is it enough? Because now it's just the architecture reference. But what about the concrete core, the actual concrete cores that implement that ISA differently, and and the causes for the pipeline stalls and where you are actually wasting cycles, that's different. Okay, well, let's say I say let's limit ourselves to this particular core. Okay, well, I've studied all these manuals for that core. Am I done? No. because that core is actually by actual different silicon vendors. They're embedded in different processors or in different systems on chips. So I have to go and study all of that for different processor. Okay, well, let's say my application is really limited and I'm just writing a VM for one particular piece of silicon, having embedded one particular core for this one particular architecture. So that's probably, 20,000 pages, right, just to target that particular piece of silicon. Oh, by the way, after those 20,000 pages, am I done? No. Because, well, there is the target operating system. So there is the ABI. Okay? Oh, how many different ABIs are just for Linux? The different variants? About a dozen? And each is like 5,000 pages again. Oh, there's another 60,000 pages for you to read. I can do the ABI, so I can generate the glue. Am I done? There are different nuances of library functions. How do I talk to the network? Because the execution agent is not, the execution engine is not all, right? I need to be able to talk to sockets. I need to be able to open files. I have to study all that, right? POSIX, well, yeah, but that's not enough. So yeah, platform quirks, all that. So, beyond living in the uniprocessor area, saying, well, portable VMs in traditional sense, well, that's impossible. Okay, well, is there a better way? There's this thing that has been going on since late 1960s and started by Zimmerman, who was not even a computer guy. He was an astrophysicist studying the sun. And they had this radio telescope in Kiel in northern Germany. The problem, what they discovered, that telescope was producing more data than any existing machine on the planet could actually process with any sort of performance, any adequate to what the telescope was producing. So they started trying to design their own chip specialized for what the telescope was giving them, and they discovered that they needed higher level tools to reason about what the processor is doing. So they realized that they cannot just use natural language to describe the semantics of the behavior of the processor. You need some formal language to describe the structure, to describe the behavior of whatever level of what's going on. What they came up with was this notion of the high-level synthesis of all the hardware and the software, starting from that formal description. So you start with your processor description language, and you synthesize the silicon. So you compile the PDL into your Verilog or your VHDL, and from there you synthesize the silicon. Well, these days you will probably start with first synthesizing for the FPGA, and then get to see. Extremely important thing. That you will probably first targeting a full system simulator from the PDL. And of course, you will be deriving the language toolchain, your binutils, your compiler, your debugger backends, your integration with the simulator, all from the same thing. So this problem of divergent interpretation of the natural language spec of the processor. And mind you, like that, those 5,000 pages of the ARM specification, right? The core ISA. That's natural language, and that's the real problem. because natural language is inherently ambiguous. How do I make sure that my reading of that ARM version 8 is the same as the guy who, the silicon vendor? And there is, especially in the absence of just one silicon vendor, like, oh, okay, well, I'm Intel, I'm producing this spec and I'm producing these chips, so that they're the same people. Post-uniprocessor, we are now in a place where these are all different guys, right? The Samsung guys who are producing the actual processors, they're not the same guys as the ARM guys who are producing the ARM spec and the cores. So there's many players involved. So how do I express this common thing? So if I am arguing about this high-level description of what the processor is structurally and what it's doing behaviorally, and I'm not really manually playing with this, or just maybe playing with it manually, but I'm reasoning using this higher level tool, well, then that divergence does not happen. Okay, so can we take a PDL and use that for producing a VM for Smalltalk? I tried something. I took a PDL system called ArchC. It's an open source. It focuses around System C, so you get things like TLM 2.0. It comes with several extremely high fidelity models that are not necessarily developed by them, but there is a whole community providing models of a number of processors. Include ARM, Spark, MIPS, PowerPC, but there's also some weird ones and some things that you wouldn't be thinking about now, such as like Intel 8051 microcontroller, this really tiny thing, and some very exotic processors like application-specific architectures that are just done for one purpose. Extremely high quality thing. Their full system simulator runs unmodifying Linux on all of these platforms. So you just take a binary. You produce, I'm going to go back to the last slide, you produce the tool chain, so all of the binutils, the compilers, everything, and you compile the Linux sources into a binary, and then you run that binary with a full system simulator, which is derived from the same PDL, and the system boots. So that gives you an idea. No. We will get to the bytecodes. No, we are running normal. Like if you want to target, for example, ARM, you are targeting real ARM. It's the question is, how do I avoid writing a VM manually? The idea is that I write this universal thing that takes a model, a formal specification of ARM, and spits out a VM for ARM.
So that translation work is outsourced to that machine instead of being your back.
Yes. You don't have, let's say you have these architectures. You don't have to do all the work of studying all that and manually porting the VM to all of them. And maybe tomorrow you want to run on some very weird, very specialized hardware that you build specifically for some weird purpose. Well, You don't do it. You don't do anything, right? It's a 30-minute job, right? You just get this PDL file, you throw it at the generator, boom, there's your new VM for that weird machine. There's a problem. The problem is that ArchC in particular, being oriented towards simulation, the instruction semantics are specified as arbitrary procedural code. You've got C++. The instruction effect is chunks of random C++. It gets your simulator very fast. But the problem is that translator backend cannot sort of reverse it, right? Like reason about what that C++ is doing for the purpose of instruction selection. So, there is another project out there in Brazil who took ArchC and extended it with something they call ACC Gem. What that is RTL level declarative semantics of the processor. And what they're able to do, they are able to synthesize the compiler backend from this combination of description. I'll show you what it looks like. Okay, so this is a directory with a bunch of models for MIPS, for ARM, for PowerPC, for Spark, for MIPS 3000. I'll show you, well, let's say, yes. Terminal up. Oh, yes. Yeah, that was the last line anyway. So here, you've got a number of files. You've got PowerPC.ac. That is a structural description of the processor. I'll just show you. So, say how many bits, the system's got some memory, there is a register bank of 32 registers, you've got some special registers there, and then, yeah, special registers, their names, and then that's just the, yeah, it says it's big endian, and this one includes the ISA. So the ISA starts with a number of instruction formats. So here's your fields, how wide each field is, what's the name of each field, and then according to those formats, then this is the declaration of which instruction uses which format. So add integer uses instruction encoding D1. Oops, I didn't mean that. Yes. So instructions, and then you've got the assembly mnemonics. That's what's used for synthesizing the bin utils, like your assembler, essentially. And then these ones, this set decoder, that specifies the actual instruction encodings. So this is your add. Okay, the opcode is 31. And, right, like these flags are they're fixed at that particular value. And whatever operands are left, that's your operands to the instruction. So whatever is specified here, that's like constants in the instruction encoding, and everything else is operands. And that's pretty much your, there are some pseudo instructions that's for assembler to be able to things, and it has things like is branch, what kind of conditions are affecting the execution of the instructions, when it is taken, when it's not taken. Things declaring whether it's a jump. So this is pretty much what you need for simulating the processor. Now, the actual instruction effects are in this thing, CPP. As you can see, these are meant to be processed, and then finally they become C source code, or C++ rather, which gets linked with the simulator. So you cannot really deduce instruction semantics from any of this because of the halting problem, you cannot even say, whether it terminates or not at all, let alone what it does. So, the ACC Gen additions, that is in this compiler info. And the interesting part, I'm going to, for the interest of time, defines your ABIs for some processors, what special registers, but for the sake of time, I'll just show you this really relevant bit. These are declarative semantics for each instruction, and that is a fragment of data transfer tree or control transfer tree. And it says, negative, that's a transfer from operand 2 negated to operand 1. And both of them are GPRs. This after colon is like in Pascal. It's the type of argument. So both of them are GPRs. So this is what the thing looks like. Now, how do we get from here to generate code? Well, all of these things, they're fragments of the data transfer tree. So, you're matching. There are several classical papers that describe how to do that. In general, optimal instruction selection is computationally intractable, and that's been proven, and there's no way around it. So what do we do? Well, one approach is, and that's these guys, 1985, that these fragments, they are considered as a grammar. So each of these each of these is a production in the grammar. So this is the non-terminal which is derived, and this is the right-hand side. And you take your, let's say, your compiled method, right? The bytecode representation. You take the RTL, which, for example, COG produces as intermediate thing, and that's some sort of tree, right? So what you do is you say, okay, well, that's a string. Let's see if that's a string in that language. So parse that tree using this as production rules. And if you're able to derive it, well, that's your answer. Now, the problem with this is, well, first of all, that grammar obviously is ambiguous, because there's many ways to calculating a result, right? That you know that there's no one way to do instruction selection. You have many different possibilities. So one way is to, okay, well, let me parse depth first, right? So you do recursive descent, and it's going to give you at least, well, you know that it's that it's not going to be exponential in time, A, and B, it's going to terminate, right? Well, the problem is that this parsing is always left biased, right? So you descend down. What's the problem with being left biased? So you descend down. Let's say you have two pieces of the tree, right? So it has the left subtree and the right subtree. So you descend left. And you say, oh, okay, well, this left piece of my tree, I've encoded it using these instructions. The problem is that once you have done that, it's too late to say, oh, no, but this is really bad, because now the result is in a register which uses, like, let's say you have left plus right. I'm sorry, I don't have a board to write here, and that limits me very severely. So I'm going to hand wave. So there's a left side. You're trying to calculate this, and then do an add. Oh, no, this result of this calculation of the left side has put it in a register for which the machine doesn't have a good addressing mode to do plus and then stick it into memory, right? So, oh, it would have been so much better code, working so much faster, if I knew while I was recursive descending while parsing my left side. So, okay, that's bad. Now, how can I do without going exponential over all different possibilities, over iterating like, okay, well, I've got 50 bytes, get all possible bytes and just select those, right? That's obviously intractable, right? So these guys in 76 wrote a paper saying that if your machine has certain particular properties, such as uniform register file, orthogonal instruction set with respect to all addressing modes available equally for all registers and for all different instructions and so on. They're specifically talking about some properties of addressing memory. So if you take a number of restrictions, then you can have an algorithm where the computational cost of optimizing the whole tree is a sum of optimizing the two subtrees. Well, certain important processors, such as Intel, do not have that properties, but some do. So, let me show you experiments that I did using Faro and Cog. So, for parsing the ArchC grammar, we now have this wonderful, wonderful thing called the JIT parser. So that gives us, we take the structural description, we parse it, that gives us smalltalk objects. The instruction encodings, that's smalltalk objects as well, thanks to a petit parser. Now, the RTL semantics go into a logic database. Let me explain why. Obviously, this whole enterprise is a large one. I didn't want to get stuck on programming all that manually and implementing all those algorithms. They seem to me, for a proof of concept, to be way too complex. So for simplicity, the first thing that I thought would be useful was back in 1997, I was playing with an implementation of backtracking in no, not this one. This. Why is it not? Hang on. It's here. Yes. Was it black? Well, no, it's okay. We don't have a lot of time. Let's skip that. Sorry. It's an image that I had from back 1997, where I was playing with an implementation of backtracking that is described in a paper by Lalonde and Van Gulik about implementing backtracking using direct manipulation of smalltalk contexts. So you've got two primitives, succeed and fail, and when you succeed, it remembers where you succeeded. That's your return point. And then you do something, and you say, oh, no, I screwed up, let me try something else, right? You go fail at this point, and it just remembers. And it's beautiful. It's less than 1 page of small talk. So now in your language, you have a really elegant way to express backtracking. And you add infinite streams on top of that, and now you have that. Well, first of all, that's code that only runs in Squeak 1. And I was like, meh, yeah, I don't really have much time for porting that into contemporary Faro. So there's Prolog V that was done by Mike Tang, and then it was ported by Balot Kirimbaev for Squeak more than a decade ago. So I ported that to Faro, well, just partially, like half of it doesn't work. But it's enough to do, it has resolution and it works, and it has unification and it works, and it's basically all you need for doing what we want in terms of tree matching. So what we do is when the petit parser encounters one of those instruction blah semantic is blah blah blah, it issues an assert into the Prolog database. And then your tree matching becomes basically a Prolog goal. Unify this tree with these known facts, which were put into the database while parsing the PDL. And I would like to give you a demo how this all works, but we're out of time. So we can, I guess whoever is interested, I can just show them. We still have 2 or 3 days here at the conference. There's some difficulties that are for the future? Well, one how do we deal with the platform ABI? The problem with these PDLs, it's really a processor description language, and ABI is fundamentally a guest concept, like in terms of guest operating system. So the PDL doesn't really. There are attempts, because people have been synthesizing compilers from ArchC and especially that, but because of the fundamental orientation, because of the fundamental initial goal of that particular PDL, it describes the ABIs very poorly. So something needs to be done for that. We need to integrate this with simulators. M5 Sim, which is now Gem5, which I have a number of interesting Smalltalk-aware modules for that being outside of the machine, you can see at the level of Smalltalk semantics what your VM is doing. They need to get integrated with COGS processor simulating facilities, like the aliens, whatever. I don't really quite up to speed with how that works. That needs to be done. Obviously, the native System C TLM simulation needs to be brought into that picture. Prolog always presents this problem. Well, how do you know that your order of rules does not lead you into an infinite loop? Or, just being, it's perfectly valid to generate, and this AT&T syntax, by the way, not Intel. So left to right, that you move from R1 to R2, from R2 to R3, then to R4, and then you finally add 1 to it, and that's for just adding 1 to register 1 and placing it into R5. Like, how do I know that? So I have to account for costs, and right now the Prolog implementation does not do that. An interesting thing is how do you bootstrap a system like that? Well, obviously, what we want to do is VM dependent. For different VMs, we want to write it specifically for that specific VM. I can think of two approaches. One is mixed mode. You have interpretation and JIT in the same VM. Obviously, you can start interpreting, and then you can, when you have enough, you can bootstrap that way, or you can just compile ahead of time just enough of the JIT that you can start, and then when you have the native code like preloaded, let's say in a special segment in your image, obviously that's processor specific, you can bootstrap that way. Do you have any questions? Okay.
Because I don't follow. I want to know if you have a feeling that do you see there is a way to reach that goal of having something that you wish to kind of rewrite different architecture? I am absolutely positive. I will, if you want, we can sit down together. I will show you how much of it is already working in actual firewall. It doesn't run the whole VM. Like, you cannot run the whole firewall on it and I can show you what is difficult. But so far, I don't see. I mean, it's just a matter of programming, I believe.
No huge showstopper. It worked, but no showstopper.
I think the proof of concept works well enough to say that, well, I don't expect further major roadblocks. Yes.
Another optimization. I mean, this tree matching. Yes, you're using it for instruction skips, but it seems like that could apply to many levels of optimization. Tree matching, right?
Yes. Yes. Well,
When are you porting to modpath? For instance.
Well, let's go to the previous slide. No, not the previous slide. No, hang on. Oh, no, actually this slide. This is what I hinted at when I said VM dependent, right? Well, this mechanism is going to be different for Faro and for ModTalk and for B. However, all the other parts, tree rewriting and parsing the ArchC, structural description of the processor, instruction encodings, all those pieces stay the same. So if you want to use that to deal with automatically retargeting ModTalk to a million different processors, I don't see how this approach would be any less valid than for any other Smalltalk. Yes.
Production virtual machines that have like small box Ruby or anything else are they're complex design exercises that for the most part incorporate a large number of lessons.
Yes.
Derived from experience and understanding of programs and knowing where it makes sense to apply computational effort and where it doesn't make sense to apply computational effort. And to some degree, that's a moving target.
Yes.
How programs change over time and such. And this seems like a very mechanical way to produce a VM, and it doesn't have it. I don't see any sort of room to bring in the sort of design heuristics. I tend to think are the things that actually make real VMs practical and useful.
It will, yes. It will remain. It certainly will remain to see. What gives a good hope to me is that people are using these approaches for producing backends for, let's say, for the C compiler. There is the ArchC guys. They have done a similar exercise for. They've done an LLVM backend using that, and it seems to be well. It doesn't. It is not as efficient as the standard, or as say GCC, or even the standard LLVM backend right now. But it's certainly not dramatically worse, and it is sufficiently complete that you can actually compile the Linux kernel and boot the executable on, or well, boot the binary on the around either on the around simulator or some other people's simulators, or on the actual silicon, or compile a number of large C programs, and it just runs unmodified on actual hardware. So yes, I guess this will need more work to be as polished as today's either production C compilers or production VMs. But there is a lot of people moving that way, and it seems like there's a number of challenges that really make a manual approach with this heuristics. It makes it very, very challenging in face of today's complexity. And every time you do this manual optimization, you introduce new complexity. And when the number of players getting involved in producing, ISA design, and then the actual silicon, and then the tool chain for it, when the number of players involved in that game increases dramatically, the complexity of that interaction makes this manual work very, very difficult. So yes, they're high-level tools, but the same can be said about any high-level tool, right? You say, oh, okay, well, the compiler is a mechanical machine that produces assembly. Well, I can always write better assembly by hand and be very clever about which instructions I select, but the compiler cannot do that. Well, yes, but there are still compilers for the last 30 years. Does that answer your question? Okay. Okay. I'm very interested in this. Like, why for Smalltalk, why a mechanical approach to producing the JIT would be less valid than a mechanical approach to producing a C compiler automatically from the processor description. I mean, it's not a whole. It's just the JIT that produces encode, and it's basically a translator. Right, and this is a well understood problem, and
One big difference is the dynamically acquire runtime type information, the actual behavior of the program, rather than being statically acquire all that.
Right. But in terms of okay. So now we're talking about optimization. Let's say right now, all the JITs that I'm aware of, what they do is they produce the binary basically chunk by chunk, right? Like there is an abstract instruction, and then we concretize that to a particular machine, right? Like HPS does that, COG does that. Hotspot does that. It's not that we're looking at the whole graph and then we are taking advantage of that type of information for more optimization there. We're just, the pieces that we're tree matching right now are very small. So if we are capable of even mechanically looking at a bigger chunk of, let's say, of the data graph, and try to optimize across the boundaries of those little chunks. So basically, you're looking at the whole at the whole bytecode sequence in a compiled method. Maybe there are sequences of bytecodes that can be optimized better than just each bytecode. So, I mean, yes, in theory, there is this question. Well, how are we very, very clever about that? But in practice, every VM that I have seen, like it doesn't go outside of this very simplistic working with this one chunk at a time, right? Sure.